In 2018, an 18-year-old undergraduate quietly dismantled one of the most celebrated claims in quantum computing history, using nothing but a laptop, a stubborn refusal to accept the wrong answer, and a proof that classical computers could do something everyone assumed only a quantum computer could ever manage. The discovery should have been front-page technology news. Instead, it slipped almost entirely out of public view, remembered mainly inside academic circles, while the broader world kept hearing about quantum breakthroughs as if this one never happened. So what actually happened to Ewin Tang's discovery, and why does it matter more today, in the middle of an entire industry chasing quantum supremacy, than it did back when she first published it? To understand the discovery itself, you first need to understand the specific claim it directly undermined. Back in 2016, two well-established quantum computing researchers, Ioannis Karanidis and Anupam Prakash, published a quantum algorithm for recommendation systems, the exact kind of technology behind Netflix suggesting your next show or Amazon recommending your next purchase. Their algorithm promised something genuinely spectacular, an exponential speed-up over every known classical method, meaning that as the size of the dataset grew, the quantum approach would pull dramatically further and further ahead of anything a classical computer could achieve, no matter how that classical computer was optimized. This was not a minor academic curiosity. It was quickly held up across the quantum computing community as one of the clearest, most compelling, most practically relevant examples of genuine quantum advantage in the entire field of machine learning. Enter Ewin Tang, an undergraduate at the University of Texas at Austin who, in early 2017, began taking a course on quantum information taught by Scott Aaronson, one of the most respected and influential theoretical computer scientists working in quantum computing. Aaronson gave Tang a specific assignment, one he fully expected would reinforce the existing consensus rather than overturn it. He asked her to try proving a lower bound, essentially demonstrating mathematically that no classical algorithm could possibly match the quantum recommendation algorithm's impressive runtime, cementing the quantum approach's advantage as a proven permanent mathematical fact, rather than simply an unbeaten record waiting to be challenged. Tang spent months working exactly that angle, trying to prove Karanidis and Prakash's original claim was airtight. And here is where the story takes its genuinely remarkable turn. Rather than successfully proving that no classical algorithm could keep pace, Tang began to suspect the opposite was true, that a classical algorithm could actually be constructed to match the quantum version's speed. Eventually, after sustained independent effort, she found it. By replacing the quantum algorithm's core reliance on quantum linear algebra with a classical technique called sampling, specifically weighting her sampling process according to the size or norm of different components within the dataset, Tang built a purely classical algorithm that ran exponentially faster than any previously known classical approach, closing the supposed gap between quantum and classical performance down to a comparatively minor polynomial difference, rather than the dramatic exponential chasm everyone had assumed was permanent and unbridgeable. Scott Aaronson, the very professor who had assigned Tang the original opposite task, later described the result in memorably blunt terms, characterizing it as a quantum computing application achievable with 0 actual qubits. That phrase captures the delicious irony sitting at the heart of this entire story perfectly. The most direct practical consequence of studying a supposedly game-changing quantum algorithm turned out to be a purely classical algorithm that needed no quantum hardware whatsoever to achieve comparable performance. This is exactly the discovery that gave rise to an entire subfield now known as dequantization, the deliberate process of hunting for classical algorithms capable of matching the performance quantum researchers claim for their quantum counterparts. Tang's specific technical insight generalizes surprisingly well, and understanding why requires appreciating a detail that often gets glossed over in more breathless coverage of quantum computing breakthroughs. Many claimed quantum speedups depend on a specific input model called QRAM, quantum random access. Memory, a hypothetical piece of infrastructure that would let a quantum algorithm access classical data extremely efficiently. But Tang's key insight was that if you're willing to assume QRAM exists and works efficiently for the quantum algorithm, an equivalent classical data structure, one that allows sampling from the input data according to those same length-weighted probabilities, can typically be built too. And once that classical structure exists, classical algorithms can frequently match the quantum runtime almost exactly, undermining the very advantage that made the quantum approach seem so exciting in the first place. So did Tang's discovery kill quantum machine learning as a promising field entirely? This is where the honest, nuanced answer diverges sharply from what a more sensationalized headline might lead you to expect. And it is genuinely the most interesting part of this entire story. Rather than abandoning quantum computing research after dismantling one of its most celebrated results, Tang continued deepening her involvement in the field. She graduated from UT Austin and enrolled as a computer science Ph.D. student at the University of Washington, where she has continued pursuing the exact same line of research that made her briefly famous as an undergraduate. In the years since her original breakthrough, she has systematically dequantized numerous additional quantum machine learning algorithms that made, similarly, bold speed-up claims, publishing follow-up work throughout 2019, and continuing as recently as 2024 with a paper titled An Improved Classical Singular Value Transformation for Quantum Machine Learning, presented at one of the field's most prestigious annual conferences on discrete algorithms. Here is the genuinely counterintuitive part of the story that even people who followed the original headline often miss entirely. Research that repeatedly disproves specific quantum speed-up claims has actually pushed the broader field of quantum computing forward, not backward. And Tang herself has been remarkably candid and thoughtful about exactly why that paradox holds up under scrutiny. Every time a dequantization result knocks down a previously celebrated quantum algorithm, it forces the entire research community to sharpen its understanding of precisely where genuine, defensible quantum advantage actually lives, separating algorithms whose apparent speed-up depended on unexamined, quietly generous assumptions about data access from algorithms whose advantage holds up under considerably more rigorous, more honest scrutiny. In other words, Tang's work has not weakened quantum computing as a scientific field. It has forced the field to police its own claims more carefully, filtering out overstated results before they can spread unchecked through less careful, more hype-driven coverage, and strengthening the credibility of whatever genuine quantum advantages ultimately survive that scrutiny. If you're finding this breakdown useful, go ahead and hit that subscribe button because we cover stories exactly like this every single week, connecting the dots most channels leave scattered. There is also a deeply human dimension to this story worth including, honestly, because it adds genuine context to why Tang's specific journey through this field has continued attracting renewed attention well beyond the purely technical details of her research. Tang's foundational thesis, titled Quantum, Machine Learning Without Any Quantum, remains a widely cited cornerstone reference for researchers working at the boundary between quantum and classical computation. In the years since her original 2018 breakthrough, Tang has also undergone a gender transition, and she now uses she in her pronouns, a detail that some of the earliest coverage of her original discovery notably avoided addressing directly, likely because she was in the midst of that transition at the time those initial articles were written. Members of the broader technical community revisiting her work in more recent years have specifically worked to properly recognize and reflect her identity going forward, treating that update as a simple matter of accuracy and respect, rather than as some separate, unrelated news story competing with the actual substance of her scientific contributions. Why does any of this genuinely matter today, years after Tang's original discovery first circulated through academic circles, rather than mainstream headlines? The answer connects directly to something we have covered extensively on this channel, the ongoing, often contentious debate over exactly which quantum computing claims represent genuine, durable advantage versus which ones simply have not yet been properly scrutinized by researchers, applying the same rigorous skepticism Tang brought to that original recommendation systems algorithm back in 2017. Every time a new headline announces a dramatic quantum speedup, whether in machine learning, optimization, or any other computational domain, dequantization researchers directly inspired by Tang's foundational methodology are actively working, often quietly and without anywhere near the same media attention, to determine whether that specific claimed advantage genuinely holds up, or whether it will eventually join the growing list of quantum results that turned out to have a classical counterpart nobody had yet bothered to seriously look for. This pattern extends well beyond the original recommendation system's result that started it all. Dequantization techniques building directly on Tang's core methodology have since been successfully applied to principal component analysis, a statistical technique widely used across data science and machine learning, along with several other quantum algorithms that initially seemed to promise similarly dramatic exponential advantages over classical approaches. A broader mathematical framework, developed collaboratively in work Tang co-authored, generalized her original technique into something considerably more systematic, giving researchers across the field a genuinely reusable toolkit for testing new quantum machine learning claims, rather than requiring each individual result to be painstakingly reverse engineered and challenged completely from scratch every single time a new paper made a bold new speed-up claim. This pattern extends well beyond the original recommendation system's result that started it all, dequantization techniques. Building directly on Tang's core methodology have since been successfully applied to principal component analysis, a statistical technique widely used across data science and machine learning, along with several other quantum algorithms that initially seemed to promise similarly dramatic exponential advantages over classical approaches, a broader mathematical framework developed collaboratively in work Tang co-authored, generalized her original technique into something considerably more systematic, giving researchers across the field a genuinely reusable toolkit for testing new quantum machine learning claims, rather than requiring each individual result to be painstakingly reverse engineered and challenged completely from scratch every single time a new paper made a bold new speed-up claim. It helps to walk through exactly how this generalized framework actually functions, because the underlying mathematical insight, once properly understood, explains why so many different quantum machine learning claims turned out to share the exact same underlying vulnerability. Tang and her collaborators identified a single unifying technical fact sitting underneath essentially every one of their dequantization results, that a specific kind of length-weighted sampling, formerly called norm-based or length-squared sampling, can approximate the results of large matrix multiplication in a way that runs independently of how large the underlying dataset actually is. That single core insight, once properly generalized into a reusable mathematical framework, allowed researchers to systematically work through an entire category of related quantum algorithms, including low-rank Hamiltonian simulation and discriminant analysis, rather than needing to independently reinvent an entirely new dequantization technique from scratch for every single new quantum claim that happened to surface. This kind of systematic, reusable methodology is precisely what distinguishes a genuinely important scientific contribution from a single, isolated, one-off result. And it is a large part of why Tang's original insight continued generating meaningful new research, years after her original 2018 paper first circulated. There is a genuinely important, sobering lesson embedded inside this entire trajectory that deserves real emphasis, particularly for anyone following quantum computing coverage today with a healthy mixture of excitement and appropriate skepticism. The specific vulnerability Tang originally exploited, unexamined assumptions buried inside how researchers measure and account for data preprocessing costs when comparing quantum and classical algorithms, remains a persistent, recurring blind spot across quantum computing research, even now, years after her original discovery first exposed it clearly and publicly. Researchers studying this exact pattern have explicitly noted that popular quantum machine learning algorithms continue to occasionally overstate their genuine advantage, precisely because the underlying computational costs of properly preparing and pre-processing input data do not always get fully or honestly accounted for when researchers present their headline speed-up comparisons to conference audiences and technology journalists eager for a dramatic new claim. This directly connects to something worth remembering every single time you encounter a new headline-grabbing quantum computing claim going forward, whether it involves drug discovery, cryptography, artificial intelligence, or any other application area entirely. The most credible, durable claims of quantum advantage tend to survive precisely this kind of rigorous adversarial scrutiny, researchers actively trying, in good faith, to break the claim using the best classical techniques currently available, the same fundamentally skeptical evidence-driven approach Tang originally brought to a homework assignment she was specifically asked to prove correct, only to discover something considerably more interesting once she followed the actual mathematics wherever it genuinely led her, rather than where her professor initially expected it to end up. There is also a fascinating, still unresolved technical debate sitting underneath this entire story that continues shaping how seriously the broader research community takes new quantum machine learning claims even today. The crux of the disagreement comes down to a single, deceptively simple question. Does QRAM, that hypothetical quantum random access memory infrastructure underlying so many of these claimed speedups, actually exist as a practical, buildable piece of hardware? Or does it remain a convenient theoretical assumption that quantum algorithm designers lean on without fully grappling with how difficult it would genuinely be to construct at scale? If QRAM turns out to be practically achievable, Tang's own analysis suggests a classical machine reading from that same underlying data structure can generally match the quantum algorithm's complexity anyway, largely eliminating the advantage. But if QRAM turns out to be fundamentally impractical to build at the scale these algorithms require, then neither the classical nor the quantum version of these algorithms achieves the kind of efficient sublinear data access they were originally designed around in the first place, meaning the entire comparison becomes somewhat moot regardless of which side of the debate you land on. Either way, Tang's foundational insight reframed QRAM's actual physical feasibility as the single most important open question determining whether any lasting quantum advantage genuinely exists for this entire category of algorithm. A reframing that has meaningfully shaped how subsequent quantum hardware researchers think about prioritizing their own engineering efforts. It is worth pausing to appreciate just how unusual Tang's specific position within the broader quantum computing research community actually is. because it does not fit neatly into either the enthusiastic quantum advocate camp or the dismissive quantum skeptic camp that so much popular coverage of this field tends to sort researchers into. Tang has spent her entire career deeply embedded within quantum computing research, publishing in the field's most prestigious venues, collaborating closely with quantum algorithm designers, and clearly possessing the technical expertise to appreciate genuine quantum advantage wherever it legitimately exists. Yet her specific contribution to the field has consistently been to systematically identify where that advantage does not actually hold up under careful scrutiny, a position that requires neither uncritical enthusiasm for quantum computing's potential nor blanket dismissal of the entire field, but rather a genuinely rare combination of deep technical fluency and rigorous, evidence-driven skepticism applied specifically to claims made by researchers working within her own broader scientific community. That combination helps explain why serious quantum computing researchers, rather than viewing Tang's work as some kind of attack on the field, have largely embraced dequantization as a genuinely valuable, constructive part of how quantum algorithm research should properly function. A scientific field that only ever produces confident claims of breakthrough advantage, without any parallel effort to rigorously test whether those claims actually survive close examination, tends to accumulate exactly the kind of overstated, eventually embarrassing results that erode public and institutional trust once they inevitably get exposed. Tang's ongoing work functions as a kind of institutionalized quality control mechanism for the entire quantum machine learning subfield, and the fact that she has continued being invited to present at the field's most prestigious conferences, rather than being sidelined as an inconvenient critic, speaks directly to how genuinely valued that role has become within the broader research community over the years since her original 2018 discovery first upended expectations. So, what actually happened to Ewin Tang's discovery? It did not disappear at all, despite receiving nowhere near the sustained mainstream media attention its scientific significance genuinely deserved at the time. It fundamentally reshaped an entire corner of quantum computing research, spawning a durable ongoing subfield that continues actively publishing new results as recently as 2024, while its original author has spent the years since building a genuinely respected academic career, specifically by continuing to ask the exact same rigorously skeptical question that made her briefly, quietly famous as an undergraduate in the first place. Does this particular quantum algorithm actually need a quantum computer at all? Or is there a classical alternative simply waiting to be discovered by someone patient enough and rigorous enough to actually go looking for it? The quieter, more accurate version of this story does not fit neatly into a single dramatic headline, the way the original quantum recommendation algorithm claim once did. But it might be considerably more important for understanding where quantum computing genuinely stands today than almost any single flashy, new speed-up announcement currently circulating across technology news. Real scientific progress in this specific field increasingly depends exactly as much on researchers, like Ewin Tang, patiently, rigorously checking whether claimed advantages are actually real, as it does on the researchers making the original, more headline-friendly claims of quantum breakthrough in the first place. It is a genuinely unglamorous, thankless kind of scientific labor in many respects, spending years methodically testing other people's exciting claims rather than making your own. But it is precisely the kind of labor that separates a scientific field capable of genuine, durable, long-term progress from on a perpetually chasing the next attention-grabbing headline without ever pausing to check whether the last one actually held up. If you want to keep following stories like this one, stories that dig past the initial headline and into what actually happened next, make sure you like this video and subscribe. Because understanding quantum computing's real progress means understanding both the breakthroughs and the discoveries that quietly, rigorously put them to the test.